Hey guys, this section we're going to keep working with parametric functions, and we're going to kind of look at all the different calculus-y things we can do with them. And the plan is get through this section. This week you have a homework assignment over this section, but I shortened it so there's less questions now. And then next week we will kind of look at this topic again in more of like an AP style fashion. Okay, so this is just the first time you're going to look at calculus with parametric curves. So we're going to do all the normal calculus-y things, starting with finding the slope of a tangent line. And that means we need to figure out how to take the derivative of parametric curves. So in order to do this, we're going to learn a new formula, and the formula is going to be modified so that it is computing a parametric function. So what we're really doing is we're finding, we're going to create a formula for dy dx. Obviously, that's how you find a slope or derivative. But we're going to use sort of like a chain rule play on things in order to do that. So we're going to look at this equation right here. And so this equation right here says that dy dt is equal to dy dx times dx dt. And why is that true? Well, that's true because if you think about just units, dx on top and a dx on bottom would cancel, giving you dy dt. Okay, so from that point, you would create the formula for finding the derivative of a parametric function by solving this equation for dy dx. So that would mean dividing by dx dt. So your formula for a parametric equation to find the derivative of it is dy dt divided by dx dt. That very simply just means take the derivative of the y equation and divide by the derivative of the x equation, and you have your derivative. Now, it's a little bit more complicated when you look at a second derivative. So if I want to take the second derivative of a parametric function, we're going to take the derivative of the derivative naturally. But the way that that works is it actually ends up just being the derivative of the derivative, and that goes on the top, divided by dx dt. Okay, there's a whole proof on this I could show you at some point in time, but for now, let's just take it as truth, and we'll come back to that later. Okay, so a curve is defined by the parametric equations x equals t squared, y equals t to the third minus 3t. And this is one of those really fun part A, B, C, D questions. So for part A, show that C has two tangents at the point 3, 0 and find their equation. So we're showing that it has two tangent lines, which is a weird thing. But remember that parametric functions, they kind of like, they can curve and loop around and do all kinds of crazy stuff. So it is possible that you have a situation where maybe the graph curves like this and comes back down and is wild like that. So maybe at this point there's a tangent line, and then at another point on that same x value there's a different tangent line. So you could have multiple tangent lines at the same x location. That's not impossible for a parametric function. So that's what's being implied here. When it says show that there are two tangents, it means that the function's kind of like curving into itself. So anyway, we're going to find the derivative first. So the derivative is dy dx is equal to dy dt over dx dt. And that means derivative of y over derivative of x. So the derivative of the y equation is 3t squared minus 3. And the x equation is 2t. So this is our derivative. And the first part of the question says to show that there are two tangents and find their equations. So that means we're going to need the slope. We're going to need the slope at each of these points. So let's start with the point 3, 0. Okay, actually, we got to back up real quick. So if you look at your equation for your derivative, it is 3t squared minus 3 over 2t. basically implying that in order to find the slope, you're going to need a time. Okay, you're going to need a time to plug in to find the slope. You don't have a time listed up here where it says at the point 30. These are x's and y's. So you are going to have to go over and find the time when the function hits the point 30. Okay, you're going to have to find the time when the function hits the point 30. So to do that, you're going to take the x value and set it equal to the x equation. Solve that, and you get plus or minus radical 3. And then take the x value and plug it in, the y value and plug it into the y equation and solve that. So you're going to get, let's see, 0 and 3. Okay, and nope, that's squared. This is cubed, sorry. Let's see here. So this would be radical plus or minus radical 3. And then you look to see where the overlap occurs. So both of these time values that were found are both including plus and minus radical 3. The y value also has 0 as an option, but that's not listed in the first equation, so that's not going to be part of your solution set. So you're just looking for the numbers that they both have in common. And that would be the time when that curve hits the point 30. Okay, so let's go back. We're going to find the slope at the point 30 by plugging in the time when it actually hits the point 30, which radical 3 is one of those times. So we're going to compute the slope by plugging in radical 3 into the derivative equation that we just computed. Okay, and if we do the math here and simplify, we would get 3 times 3 minus 3. So okay, reduce 3 over radical 3, and if you rationalize to take it even a step further, it would just be radical 3. All right, let's do the same thing again with the other time value that we identified. So we're going to find the slope. Let me move this down a little bit. We're going to find the slope at negative radical 3. Okay, again, same idea. We're just plugging that into the derivative equation, and that is going to give us the slope at that location. So is it going to be a whole lot different than our last slope value? I don't think so. So the top is going to still be 6, and the bottom is going to be negative 2 radical 3. So this would simplify to just negative 3 over radical 3, which is going to rationalize and become negative radical 3. Okay, if you read that part of the question again, it says also find the equation of these tangent lines. So that means you're going to do one extra step for each of these slope values that you just got, and that is using the point slope formula. So you're going to do y minus y equals m times x minus x, and then maybe even solve it for y. And now you have your tangent line equation, and then just repeat again down here for your other slope value. If I could write today, that would be super. Let's try again. So this one was just a negative radical 3. The x value was 3 and the y value was 0. That was given. Okay, so part A is done.